All right, as we start day 12 here, lesson 4.1b. So this is just a little extension of these middle school and these Algebra 1 ideas for proportions. Just like we did in 4.1, we're just going to deal with a little bit more, some word problems, or some other scenarios that might not just be straight in our face algebraic like we saw in the homework for 4.1. We're actually going to start with a warm-up. Now this warm-up is going to be very popular as we move throughout the unit. There's always one problem that I try and keep as more of a challenging problem, something to make you think. So this will be that problem. So make sure you come back to this video if you need some help solving this problem. Now let's add some color to that star. So this will always be a problem, just kind of how we started with that, the picture going into the 5x7 or 8x10 frame. We have a picture that's getting bigger and bigger and bigger, and we want to know, is it going to fit perfectly in this rectangle? So it says, for advertisement, Brandon plans on blowing up a 5x7 poster and plastering it on the side of a building that is 120 feet by 85 feet. So right now I've established one thing, that this picture is 5x7. So that'd be 5 inches by 7 inches. And then the building is 120 feet by 85 feet. Now, maybe this is 5 feet by 7 feet. It looks like I forgot to put the units in. But whatever we deem it, the units do have to be the same. So I'm going to pretend like this is 5 inches by 7 inches, just like a regular picture would be. So if I zoom in down here and say that this is 5 and this is 7 inches, we immediately want to convert that into feet. Now, since 5 inches is less than a foot, we're going to get a decimal. So instead of doing that, we can take the 120 feet and the 85 feet and turn those into inches, which will give us bigger numbers. But I prefer bigger numbers than smaller decimals in a problem like this. So there's 12 inches in every foot. And if there's 85 feet, that's just 85 times 12, which is 1020. And then we did it again, 120 feet, 12 inches in each one of those gives us 1,440 inches. So back to the problem. He wants to make the image as big as possible without distortion. So without distortion means I cannot just drag this image and make it 5 inches and drag it all the way over to 1,020 inches and then drag it from 7 inches all the way up. Remember when we tried to get the Steve Carell or the Michael Scott picture in the 8x10, we just dragged it however we needed to fit perfectly. We don't want to distort the image, which means I need to come in here and grab it from the corner, and I need to keep making it bigger and bigger, meaning both dimensions are growing at the same rate. So maybe 5 inches and 7 inches, maybe now this is 10 and 14. I doubled them both. Or maybe I tripled it to 15 and 21. Or maybe I did times 10 and I did 50 and 70. All of those are valid proportional picture sizes. What we're trying to figure out is, if I keep making this picture bigger and bigger, will it fit perfectly in the wall space given as is on the side of the building? And how we can check that out is we can say, is 5/7 proportional to 1020 over 1440? So will it fit perfectly? That's what we're trying to figure out right here. So if we do our cross products, 5 times 1440 is 7,200. 7 times 1020 is 7,140. It's actually pretty close. It's off by 60. Which means when this thing gets bigger and bigger, it's going to look like it fits perfectly. But one of two things is going to happen. There's either going to be extra space on the top and bottom or on the left and right. And here's what we mean by that. If this thing maxes out and it hits the top, then it's going to leave this extra space over here. Or if it maxes out and hits the right-hand side of the building first, then we have this extra space up top. There's going to be extra space somewhere because we just showed that it did not fit perfectly. So that's what we're going to try and figure out. What is going to happen first? Is this 5, 10, 15, 50, is this going to turn into 10, 20 first? Or is the 7, 14, 21, 70, is that going to eventually get bigger and bigger and turn into the 14, 40? It's not going to happen at the same exact time. One of them will happen first, leaving the extra space. So here's what we're trying to figure out. There's a couple ways to do this. We can say 5 doubled to 10, we tripled it to 15, we multiplied it by 10 to get to 50. What would we have to multiply 5 by to get 10, 20? So if you think about that, what do we have to multiply 5 by? So 5 times some unknown number is going to equal 1020. So what is this secret multiplier? How big does the picture have to get to turn 5 into 1020? So 1020 divided by 5. That means that picture has to get 204 times bigger for this horizontal distance to max out to 1020. So that's one scenario. What if we do the other scenario? What's it going to take for 7 to turn into 1440? So 7 times some unknown multiplier is going to turn into 1440. That's going to give us x equals, now it's close, 205.7. We know that this is not going to be the same number. If it was the same number, then this would fit perfectly. That's what we just proved up here. So which of these is going to happen first? Remember, this is how many times bigger that we want to make this picture. So here I made it 2 times bigger, 3 times bigger, 10 times bigger. What's going to happen first? 204 times bigger or 205 times bigger? This one's going to happen first. So this is our winner. Because it's smaller than the 205. So that means that our picture that's 5 by 7, the 5 is indeed going to turn into 1020. What is the 7 going to turn into? Now you can think of it two ways. We already know that this is going to get multiplied by 204. So that means we have to multiply down here by 204, which gives us 1428. Or you can do cross products. Five x equals 7140 divided by 5. X equals 1428. Same thing. Regardless, that is how much space will be left over. So that means our image is going to go from 5 by 7. The 5 is going to max out at the 1020, but we're not going to quite make it up to 1440. So our image is going to be 1020 by 1428. That's how big the picture will be. And then we save some space up the top. Maybe we can write something up there for the advertisement. All right, so you'll see that problem in the homework. The first time we do it is going to look, it might look intimidating, but really it's the thought process behind it. We're just trying to figure out how many times bigger does this image have to get for either the horizontal distance to max out or the vertical distance to max out. And it's just simple division to figure that out. All right, so let's move on. So there's your homework from yesterday. And then 4.1 part 2. I've been calling it 4.1 part B. And we're going to start with word problems and scale factors. A triangle is 20 inches high and 5 inches wide. So you should already be thinking of a ratio because we're just comparing two different things right now, two quantities, height and width. So it's 20 by 5. So right there, we have a complete ratio. And what I want us to do that's going to be helpful is keep track of your ratio quantities, mainly the units. What is up top? What is down below? Now, on this first fraction that you create, you actually have the freedom to put whichever one you want in the numerator and denominator, as long as you take note of that. Okay, 20 is the height, so 20 high, 5 wide. That means when I set up my proportion, any number that I put up here has to represent height. Any number that goes down here has to represent the width. So if it is reduced to 1 inch wide, so 1 inch wide tells me that's a blue number. So 1 inch wide. How tall? So we don't know how high it's going to be. That's where our x is going to go. There are 4 different ways that that could be set up, because we can flip both of those fractions. We could flop the fractions left to right. It doesn't matter as long as our cross products give us 5x equals 20. And x equals 4. So 4 wide. So 4 inches wide. So I'm going to challenge us in this next one to make sure we understand what our numbers represent. It's important to label the numbers. So a baseball team played 154 regular season games. The ratio of the number of games they won to the number of games they lost was 5-2. Now look how they wrote that ratio. Order matters. They said the number of games they won to the number of games they lost. So the number of games they won, 2. So 2 is like that colon. So that means 5 is wins, 2 is losses. So we have to understand that, the wording there. How many games did they win? How many games did they lose when we're comparing it to the 154 games? So if we immediately jump to saying 5/2, then we have to make sure we say 5 is the wins, 2 is the losses. So if we have wins on top and losses on the bottom, where would we put the 154? 154 is a combination of the both. A whole season of games is a combination of the both. So right now we see that there's something flawed here. If the 154 is going to be in play, the 154 is a total. So we need a total here. We don't want to compare wins to losses. We want to compare wins to total. So let's rethink this. Here's your basic setup that you want for a proportion. You basically want two fractions that are going to be equal to each other. We need numbers in 3 of the 4 spots. 1, 2, 3, 4. Sometimes it's popular to put the x in first because we want to know, what are we looking for? We're looking for how many wins did they have out of 154 games. Then we can come to here and say, well, we know that they win 5 games out of a total of 7 games. Now we can do our cross products. So that's 7x equals 770. Divide both sides by 7. X equals 110. All right, number 3. A skier is skiing down a hill with a 7% grade. So a 7% grade is a way to kind of measure slope. You might see that on the side of the road. You might see, if you're going down a hill, you might see a sign that has a 7% or a 3% grade. It's mainly for trucks, but it just basically tells you how steep an incline is. So a skier is skiing down a hill with a 7% grade. If the skier's elevation decreases by 858 feet, how far has he traveled forward? So there's 2 quantities that are being compared. Elevation, which is vertical up and down, and then traveling forward, which is horizontal. Because in order to go in a downhill diagonal way, you have to move both vertically and horizontally at the same time. That's what gives us rise over run. So one thing that we have to be able to understand is this 7% number is a combination of both quantities. So I'm going to make it a pink right there. 7% is both vertical and horizontal at the same time. And the reason I say that is because 7% as a ratio is 7 out of 100. So now we've exposed the two numbers. And since this is slope, this is rise over run. So if we measure slope in here and say we go down 7 every 100 forward, you don't even need the negative as long as we understand that we're going down. Then how far will we move forward if we're going down 858? So I wanted to give you guys that visual, that geometric representation, because as we get through this unit, our problems will look more geometric only. So we'll change our word problems into more picture or visual problems. So these fractions are going to be rise over run, 7 over 100. We want to know how far are we going to run, or how far horizontally are we going to move if we go 858 feet down. So all we're saying is this slope this fraction has to be just a bigger version of this fraction, because this slope never changes. So 7x equals 85,800. Divide both sides by 7. We get 12,257, so 12,257 feet. All right, so one of the words that we're going to use from here on out is this idea of scale. Okay, so we have some model cars up here, and we're just scaling down this model car. Just like we are doing with the original picture, we scaled it up to fit a 5x7, or in today's warm-up, we scaled that picture up to be on the side of a building. Those are called scale factors. And in that warm-up, we were trying to find that perfect scale factor. So in order for an object to expand or shrink without distorting, a consistent scale factor is used to change all dimensions. To change all dimensions. Usually where we see this idea of scale factors is on a map. Usually we'll have some idea down in the bottom corner. And usually we would do this with rulers. So we're actually just going to talk through this, that we would be able to figure out the measurements on this map, because whatever we measured on the map, we can convert it to real life by measuring the scale that is down here. So let's say that was the scale. So every time we measured this, let's say it was 200 feet. So we would need that scale factor. So basically that's scaling everything down, or it's scaling everything up. Now we're going to skip over the things that use the rulers. for this section, since I'm not going to assume that you guys have a ruler or be there to answer any of your questions about using a ruler. Same thing with the protractors in the last unit. That means that we are going to skip this problem. And that takes it to the homework. So in the homework, I want you guys to focus on number 1, 2, and 3. Make sure you pay attention to what's in your numerator and what's in your denominator. Okay? See if you can set each of these up like this. Of the 4 positions, 1, 2, 3, 4, you'll have an X that goes in one of them. You should have numbers that go in the other ones. But make sure you understand the units that go on top and the units that are going to be on the bottom. If you can get that correct, if you can say that these units match these units and these units match these units, you have a much higher success rate of setting these up correctly. The solving part's simple. It's really the setting up that we're focusing on in 4.1b. Number four, we're looking at a real world situation here. So basically, we have a price for 20 ounces, a price for 32 ounces, and a price for 44 ounces. As the ounces increases, the amount of money does not increase in a linear way, because as you buy more, it gets cheaper per ounce. So we want to know, if you were to compare these prices, what's going to be the best buy or the better buy, meaning which one's giving you a similar amount of fluid or liquid at a cheaper price, because we're comparing them right now for 20 ounces, 32 ounces, and 44 ounces. What if we compared them all to a similar, like 1 ounce? How much would it be for this price if it was just not 32 ounces, but 1 ounce? Not 20 ounces, but 1 ounce. Not 44 ounces, but 1 ounce. Then we can compare them all and see which one's the best buy. Number 5, this is like the skier problem. Okay, we're dealing with slope. I'm just going to set this up a little bit for you. It says at one point the ball is 10 feet high. At another point, the ball is 4 feet high. So that's a vertical distance that we just traveled there. So it went from 10 feet down to 4 feet. It went from 10 feet down to 6 feet. So it dropped 6 feet. So 6 feet it declined, or it's a 6-foot decline. We want to know, how far did the ball travel forward? If it went down 6 feet, how far forward did it go? If we know that it travels at that slope. Okay, so compare that to the skier problem. Number 6 is just like the warm-up. And then you can skip that map problem. All right, make sure you guys email me with any questions, tune into any of the office hours, contact me if you need any one-on-one time. Just make sure you guys are understanding these problems.